So just to start off with, I'd like to illustrate my project by this short video, which was taken by Alma in Chile, and it's of Ardorados, and you can see bubbles 75 times the size of the sun, which are convecting, so they're rising to the surface before sinking again. And this is a variable red giant star. It's a low mass star, but this just shows the applicability of convection within real stars. Now, I was modelling stars, modelling massive stars and convection which occurs, and I was investigating the impact of using the approximation of time-dependent convection by MESA, a stellar evolutionary simulation, to see how that played out. Was it physically accurate, or more physically accurate than a previous method of modelling convection? So first of all, what's massive star evolution? Well, we start off with hydrogen, a hydrogen star, and this hydrogen then fuses to make helium, and then we get from helium we get carbon and oxygen. From there, oxygen, neon, and magnesium, and then we get silicon and sulfur, and finally, in the centre, we build up a core of iron. Now, this evolution happens so that we get smaller and smaller layers on the inside. So this is not to scale. It also only happens within stars with an initial mass of approximately 8 solar masses or more, and that is what defines a massive star. Now, in the simulations that I ran, there were 20 solar mass models. Here we go. What is a stellar model? Well, a stellar model takes into account all of these different ideas about stellar evolution. It takes in all these equations. There's equations behind all these words. So we've got mass continuity, mass conservation, gravity, hydrostatic equilibrium, I should say, and energy conservation, as well as many others. And it takes all these ideas together. And then, so in my case, I was focusing on what we got out when we looked at convection. So this is what's traditionally modelled using mixing mode theorem, or MLT. So in MLT, we look at a bubble a temperature constant bubble, and we model this moving in radius. So moving from within the star to cooler areas, and how long it takes to integrate into the environment. And we model that using these temperature gradients with respect to pressure. Now, specifically, looking at the equations. So we've got these values here. So we've got opacity, density, gravitational field strength, gravitational field strength, pressure, temperature, and specific heat at constant pressure. So these are all local values, so at that specific radius. This is a one-dimensional model, so our dimension is radius from the centre to the outside of the star. And from those we get these gradients. So we've got nabla, which is temperature with respect to pressure for matter at a given level. Then nabla prime, which is within the convective elements. Nabla adiabatic, which is this gradient but for matter moving adiabatically. Nabla R, the gradient but for movement of energy via radiation pressure, so movement with photons, movement via radiation. And nabla mu, which is the molecular weight gradient with respect to pressure. And this is just an example of one of these, what these nablas really mean. And from these we get out these two criteria. So either we look at the Ledoux criterion, where we don't assume chemical homogeneity. So we include this nabla mu term, whereas Schwarzschild's criterion, which is what I used, does assume this chemical homogeneity. Okay, so from that, let's move on to time-dependent convection. So this is as you might say, an extra level, And what we look at is the dynamics of convection, so growth and decay of this convection. So the start and the end, it varies a little bit. And we get these from the fluid equations. Now, fluid equations, obviously, they're three-dimensional problems, not one-dimensional. You can see that in this figure from Rizzulti et al. 2023. And this is just a slice through a three-dimensional model. So with radius on this axis here, and you can see these convective cells and how they evolve over time. This color scale is fluid speed, and what MESA aims to do is it aims to accurately model this, but in one dimension. And this is what this project was all about testing whether this was in fact physically accurate. So in order to analyze these models, I used Kippenhahn diagrams. They're very important things. So this is just a mixing leg theorem model as an example. And you can see convective envelope and convective core regions. This is just convective velocity in the colours. And we start with helium to hydrogen, hydrogen to helium, which is this core region here, then helium to carbon, which is here, and that goes off into a shell, then carbon to neon and oxygen. Then after that we go from neon to oxygen, again into a convective shell, oxygen to silicon and sulfur, and then finally silicon to, in a roundabout way, to iron, which goes off into the shell here. And as you can see with this logarithmic scale on the x-axis, this gets shorter, so we get shorter time periods over time. We also get higher velocities over time as we go from the left to the right, higher convective velocities. So that's just the general trend that we expect in all models. Now, findings-wise, there were some overall indicators which I looked at. So you can see here that these lines track very nicely, but over time they get further and further away, and in fact they get into these two groups. Now, fine signifies short time stepping, so that's a high resolution model. Coarse, the opposite, low resolution. TDC, time dependent convection, and Cox is just mixing leg theorem. So you can see here that the coarse lines and the fine lines track very well together, whereas TDC and Cox don't separate much. So that suggests that really the main determinant of difference is the resolution of the model, and we'd expect that to differ as we go along because of over time stepping becomes shorter, and therefore the resolution will matter more over time. Also, I observe a shell merger. So these are both low metallicity models. We've got that's low amounts of initial metals within the model. So mainly hydrogen at the start, and we start with so at the bottom we've got mixing leg theorem at the top, TDC, time dependent convection, and you can see the main difference here. So we've got a slightly larger shell merger here, so in a larger increase in radius. This is just again convective velocity, and another thing to note is that all the models, so the profile of convective velocities is slightly different. Went from a low to a high to a low in TDC, whereas with Cox it went from a high to a low. So that, yeah, again that was another slightly different treatment within these two models. But generally speaking, these models are very similar. They do look quite similar, which was the main finding of this study, of this project. So the main limitations, well, time was one of them. I typed this little thing into terminal, and I'd be like, is it ready yet? No, it's not. It's even 6 days. In fact, with three-dimensional models, it can take months. But yeah, I still got bored trying to wait for my model to run sometimes. Also, future work would be to compare these three-dimensional models to the one-dimensional models to see whether there are differences, or whether the one-dimensional approximation that MESA has is actually quite accurate to the three-dimensional model. So I'd just like to finish by saying thank you to the physics group at Keele for being so welcoming during my internship. Thank you to SCPS for providing the internship. Thanks to Emma and Vishnu for being so helpful and providing so much guidance throughout. And thanks to Raphael again for all your guidance and for facilitating the internship. So this is my bibliography, and thank you for watching.